So today, I think we are going to work through the winning solution for the uh, WSDM conference, WSDM Cup competition. It is mainly focused on multilingual user preference modeling. I have also shared this blog in the chat. So you see, it's posted 2 hours ago. So I just trying to organize all the put together the content that has that tries to have everything at the same place for you to understand the why we need user preference modeling and how it is leveraging LLM, and then more looking into the winning solutions of this competition of how we can model the user preference. Uh, so this is a link to the cup. So if you're able to open the media page, and this will directly goes to the Kaggle competition of this. So it's already closed in March, and this conference is also held in Germany in March. So the competition is done, conference held, and I think it's very interesting to see the final leaderboard to see about 800 over 800 teams joins the competition, and then the top performance we can get is around like 71% accuracy of how we can model the user preference. Okay. Before diving into the winning solution, I want to first introduce a little bit about like why we need preference modeling and how it is helpful for LLM training. Right. So why preference modeling is important? Because we all know that LLM, if we want to improve the user experience of LLM, right? Like using LLM as a chatbot or as a human assistant, we want to align the LLM outputs with human preference. So usually in the LM training, there is usually like trained, like say pre-trained vast internet data set, and then further fine-tuned on some supervised data sets, right? But people also say that it's misaligned with the human values or preferences to to make the output really useful. And then there's many proposals, for example, the Instruct GPT using the reinforcement learning with human feedback, reinforcement learning type of approach to incorporate the user feedbacks labels to further fine-tune the LLMs so that the LLM is able to align more closely with human judgments in terms of the helpfulness, in terms of like being concise, right? To generate the useful output that aligns with the human judgments. And also there's also a threat on in terms of the LLM fairness and safety, right? Because the LLM may without alignment, the LLM may generate biased, unsafe statement. So this preference alignment is also to help reduce the common issues, including some hallucinations, generating biased content and unsafe statement to make sure that we have AI safety. And the LLM is able to be really reliable and safe for the users and society. Uh, and then why we need preference modeling is, well, in order to do this, right? You see, like in order to connect human preference, we need to connect the labels from humans, right? Like human needs to say, oh, this is better. Oh, this LM output is better. This LM output is worse. Human needs to provide these labels. But can we train a model to directly model the user preference labels so that we can do the large scale feedback from the preference model? It's kind of like automating the human labels for the preference, right? So that we can have a preference model and to provide the feedbacks to the LM to improve the model's alignment with human preference so that we can also replace the need of extensive manual annotations. So that's where why we need human preference and why we need the preference modeling. Uh, so in the end, it's like if we are really able to model the human preference very well, then we have very good feedback signals to train the LM to train the LM further without extensive manual annotations and also improve the LM towards the generating more friendly, more useful, helpful, and safer outputs that aligns with human values. So this is the why. And then the next, I also put like how usually user preference, say if we have the user preference labels, no matter it is directly from humans or from the preference model, right? So it predicts, like say, which LM is better. Say if we have the user preference, then how it is leveraged in the LM training. So there are usually like two ways to optimize the LM performance. So one way is so one way is like we can directly do the supervised fine-tuning to fine-tune the model on the demonstration data. So this is like I think you are all familiarized with the like just supervised fine-tuning, but it's a very labor extensive task, right? So the labor needs to demonstrate what is the expected response to this prompt, right? Like explain the moon landing to a 6 years old. And then the labeler needs to write the full paragraph to that. And then once we get a human paragraphs, we just do the supervised fine tuning of the model so that the model can generate the similar paragraph to that question. But you see, this is like a very labor intensive task. And then people identify a way to say, oh, instead of doing this, like collecting the extensive labels, how about we just ask humans to rank the outputs, right? So we can prompt the LLM multiple times, generate multiple outputs, and then we ask humans to say, oh, which output is the best to you? I think if you use the ChatGPT, they usually sometimes like just output two outputs to you, right? Ask you like A or B, like which option is better. So that is the preference data, preference label that they trying to collect from humans. And also it's a much easier labeling task, right? Like instead of writing the full paragraph, the labeler just need to provide which is better or provide a rank of the outputs from the LLM. And then this labeling data, like kind of like a rank of the outputs, is used to fine-tune the LLM, also called the policy model, so that the LLM can optimize the can provide the same ranking as humans, kind of reflecting the same or aligned with the human preference this way. So usually like this is how the data is connected and how the LLM is trained using this preference data. So there are two paradigms of doing that. So one is as I mentioned, is the reinforcement learning with human feedback, right? So this is proposed by the initially proposed by the Instruct GPT. So this step usually happens after the instruction fine-tuning. So instruction fine-tuning is you have the exact like input outputs, right? And then you do the supervised fine-tuning to predict the target output. While over here, the preference alignment, you apply a reinforcement learning with on the preference labels, like to say which is better, so that you can gradually improve the rewards. So reinforcement is all about rewards, right? So you want to iteratively improve the rewards in the end too, and the reward is reflected by the human preference labels. And actually, there's another direction right now I see going on is just direct. They call DPO. Oh, it's become large. So it's called DPO, direct preference optimization, which removes the need of reinforcement learning and treat it as a supervised fine-tuning approach. So it's like after you finish the pre-training, right, on the unlabeled corpus, you directly do the optimization using the base model on the preference data. So a common like algorithm is called ORPO. It's like odds ratio preference optimization. So I think you can do here. So I just ask ChatGPT what is objective what is objective function that the ORPO is trying to optimize. So if you see the formula here, it's trying to so W here is the win. So this is a win response. This is a lose response, right? So it's more like pairwise label. So this is the response that the human say this is a win, and this is a lose, the response. And then you want to maximize the soft probability of given the prompt. You want to maximize the probability for the winning response. And then it has a second loss, which is trying to the intention of it is to encourage the model to prefer chosen responses, basically the winning responses over the rejected or losing responses by maximizing the odds ratio between them. So it's like not just focusing on the win response, but also trying to push the model to prefer, right, to choose the winning response over the rejected or losing ones by using this formula. So yeah, so I think if you want to deep dive um, deep dive into this algorithm, I think yeah, that's the quickest way just to chat over here. Uh, so that's the overview. And then let's look into the competition. So hopefully this will set up a good background for you about like why we need preference modeling, and once we get the preference labels, how it is leveraged in the LLM training. Yeah.
Yeah, that's a good question. So,
Uh-huh.
is ORPO or this newer step? I imagine it's computationally smaller task to achieve, but is the quality better or is it similar to RLHF? And are they used both? Is one of them used?
No. So my understanding right now, this is exactly still like a supervised fine-tuning. It's just that it's going to take two responses, right? So winning ones and rejected ones in to optimize this training objective. To optimize this training objective here, there's no reinforcement learning. It's just a direct supervised learning on
Okay.
the preference, on the pair of responses from the,
So it's
yeah,
much simpler, I guess,
much
computationally.
simpler. Yes.
But quality-wise, is it competitive with
Some
RLHF?
papers say it is. Some papers say like direct preference optimization is sufficient. We don't need reinforcement learning for human preference modeling for to learn the human preference. So the DPO paper claims that, but I think it's still under development, or maybe I think it's just two competing threads with each other.
Okay.
It's hard to say which one like fully wins over the other. It's I think in the preference modeling space, I think it's competing. But in terms of reasoning, right, like the chain of source tokens, in terms of the reasoning space, I still think the reinforcement learning still has the advantage there. Trying to balance the exploitation and exploration, right? That's the essence of the reinforcement learning. Well, I
Yeah.
don't think the supervised one can provide that. Yeah, I think it will be interesting to see the latest on the DPO thread. It does save a lot of computing resources, right? So you basically skip this super fine-tuning, and you also reinforcement learning is very hard to train and not very stable, hard to converge sometimes. So if you can be replaced with the direct DPO, then yeah, it will save a lot of the training resources. Okay, then let's get back to the competition. So this competition is a very simple objective. So this task in the competition is to predict which response a user will prefer given two LLM outputs. So you just so you provide the prompts to the LLM, and it generate two outputs, and then the user will decide which is the winning response, and which should be rejected. And also another thing about the competition is interesting. So this is also a code competition because I think it's trying to limit the training resources and also the inference time to make sure that it's a small and yet effective model, so that people do not just put lots of weights, like put too many weights into the just try a big model and maybe solve the problem. I don't know, but there will be some computing resources constraint on this competition, to make sure that the model is within the reasonable small model, and to see what is the limit of that small model, modeling the user preference. I think the inference time is the most important. Like you need to complete the inference in 12 hours, on the test data set. And also it does not allow internet call, so definitely not able to call like OpenAI API or Cloud API. So yeah, so no API call, so it has to fully relies on the model itself. But also it allows the attendees to use the freely publicly available external data. So not just using the training data the competition provider provides, but also any public open data sets, and also open to use any pre-trained model. The evaluation matrix is also straightforward. So because it's just a binary label, so you can think about it as a binary classification, right? And then the metric competing is just the accuracy. So just compare the preference model. So preference model also outputs out of the two responses, which win, right? Model A or model B. Human is the same output. Human judge will also provide, okay, model A wins or model B wins. The response A wins or response B wins. And then just compare the two columns of the binary labels and calculate this accuracy of correct classification. So it's a binary classification. Correct classification divided by the total classification. It's kind of like also the agreement rate with a human judge. Yeah, so that's the constraint, and that is the task and the evaluation matrix. And then the data set provided is from the chatbot arena. That has about 48,000 training examples across languages. And then each example will include a prompt. So each example include a prompt. So the same prompt was given to both models. And then there will be a response from the model A or B to the given prompt. So there will be two responses to the prompt. And then there will be a human judge to say which one is better. So the winner, like A or B, right? So this is the one choose the target column. Yeah, so this is the judge, and this is the identity of the model A or B. Yeah, so this is just like to say the winner is like model A or B. And also what is the language used in that prompt. So the training data also provide the prompt is in which language. So the test will be just a prompt, right? So the prompt to the LM. And then there will be like two responses from the prompt, corresponding to the prompt, and then you need to predict which is a winner, A or B, right? So given two responses, A or B, you need to predict which is the winner, also A or B. So that's a data set setup. Yeah, I think it's also straightforward if you just keep thinking about it as a binary classification problem. So just you want to select the winner out of the two responses. Okay. And if you look at the leaderboard, right? Yeah, so the leaderboard, actually the score is very close. So the top two winner is almost exact the same score. So I would say the first winner has some luck in it that they have slight advantage over the second winner here. And then they have a slight gap with the third and fourth place there. Yeah. And this is the accuracy, right? So this kind of tell, oh, with a small efficient model, kind of the upper limit right now on this data set is about only 71% or 71.6% accuracy aligned with the human judge. Yeah, question?
Yeah, yeah. I just checked out this chatbot arena, and it's basically a radio application that you can chat and you get two responses from two
Yeah,
unknown models, and you get to rate which one is better or worse. Do you
yes.
know what kind of is it just general chat, or is it like specific task, for example, like code creation or translation or summarization? Is it like a specific task they have in this 48,000 training sets
I
or
think it's pretty diversified task. There may be some distribution of what the task category it is because the winner also saying that they look into the task set and then they also specifically select some task categories that are similar to those task data set. So I guess there will be a distribution of tasks, but it's not very limited to coding or math, but more of the general writing because the general right because for the coding or math is strict, is deterministic of which is correct, while the general writing, right, storytelling and just providing a response to whatever questions is put out there, that type of task really requires human preference, not
nice.
the strict answer one. Yeah.
Got it. Okay, thank you.
Yeah. So this is then the first place solution. They also put their solution here. So if you click the oh by the way, if you click the solution here, so you can directly jump into the solution over here. But it's written in a little bit brief way. So if you need to do some research of some of the words they say, like soft label, out of the fold. Yeah, it's like writing in a very brief way. I trying to complete the full view there, but I there may be still some misalignment because this is just based on my judgment of what they put over here. So overall, so the first place is using the full sequence classification model, and you can choose to select any model as the base model for this sequence classification, right? And then the input to the sequence classification is just the prompts and two responses, right? Because you want to see which responses is correct. And then some responses may be too long, and then they also do some truncating from the middle in case if the sample exceeds the maximum length. So they do kind of an equal truncating to keep a fixed length for both of the responses, and then concatenate them together as the input to the classification model. So there are several stages they put. They do a pre-training, but the pre-training is not the classic unlabeled pre-training. It's still a full fine-tuning of the base model. So they choose the like a student model and teacher model. Why they are doing this is because the computing resource, right? The competition, that the maximum 12-hour inference, right? So you cannot just upload a very big model or else you just go exceed the limit of the inference time. So they choose a student model that can fall within the inference limit, and then they also in order to train an effective student model, they plan to train a teacher model and then let the teacher to distill to teach the student so that the student has comparable performance with the teacher model. And then in the pre-training, they train both student and teacher base. The data sets they use some public external data sets actually. So one is this is a DPO data set, so the DPO, right? So ORPO, DPO, yeah. So this data set is originally proposed for the direct preference optimization algorithms. So you see the data, you can also click the link to go to the Hugging Face data sets. So you can see what is the data looks like, right? So you have your prompt, and then you have your different responses, two responses, and this is the winning one, chosen one, this is a rejected one. So this is kind of like a pairwise preference data set. And then they also have a Chinese dataset, the ultra feedback Chinese dataset, I guess, to improve the performance for Chinese language specifically. And this dataset is same as the regional, like there's a ultra feedback dataset specifically for the kind of the preference and also scoring the outputs, right? In this type of data set, it provides a very detailed assessment of the LLM output, including the helpfulness, instruction following, truthfulness, honesty, etc. And then the scores is actually synthetically generated by the DeepSeek V3 model. So if you see over here, like this is the instruction, this is the model, and then they run the model to get the outputs, and then they have the ratings for the response for the model. Yeah. This is their pre-trained full fine-tuning data sets, and then they do the full parameter fine-tuning. Although I don't know why they didn't choose the efficient fine-tuning. Maybe there is still some tiny differences. But at least they say like they do the full parameter fine-tuning using this. So this is a algorithm to be more like efficient or memory saving for the training. And then, yeah, so this is just the parameters they choose to how they train both the student base and the teacher base based on the QAM 2.5. Okay, so that's the pre-training one. And then the second stage, they focus on the teacher training. So the end goal of teacher training is able to provide labels, right? To provide the labels to train the student model. They do a fivefold of the data set and then train the teachers 5 times. So it's like fivefold, right? So you split the data sets into five portions or five folds, and then you train the teacher on 4 folds and then predict on the remaining 1 fold there. Right, so this is like how you can get the predictions for the data sets, right? Without overfitting. So basically, you still have a holdout data sets, and then you just train the teacher on the 4 folds and then predict on that 1 fold, and then using the labels on that 1 fold as the labels for the student model. And then in the teacher training, they use this human preference data set. As you see, this is also like this is model A, model B, different type of model. This is a prompt, different responses, and also this is a human annotated, I think, a human annotated data set to say which model wins. So this is this data set, and then they also use the data set for this challenge, right? So for the chatbot arena to train the teacher model. So you see the teacher model actually is just they claim is about just 100. Yeah. So just roughly like a 100K labels. But you see on the student distillation, they use a lot more labels to train the small model. This is also because the large model, like the 72B, with a smaller set of labels, you can already get very good performance. Well, in order for a smaller model to get comparable performance, you need to have a lot more labels. So that's why usually people also train a big model first, right, with a smaller set of labels, like higher quality human crafted labels, right? And then use the teacher model to synthesize the label. But you need to collect the synthesized label a lot in order for the small model to have comparable performance. And then let's move to the stage 3, which is the distillation. So I also want to touch a little bit on what does the distillation mean, right? The distillation, so you have your ground truth, you have your inputs, say the concatenated LM, the two responses from the LM, we're trying to distinguish which wins, right? So you pass it into the big model, and then you will get a soft labels. Soft labels means is the win rate, right? So say the soft label is if the score is 0.8, so that is the win rate for response A. And then it's likely to say the response A wins, right? If the soft label is 0.2, it means that it's likely the response B wins. So this is soft label. It means like it's a probability score, like from the big model. And then this is a small model. You can pass the same input to the small model, and the small model will also give you some soft predictions, right? And then you want to minimize the differences between the big model output and the small model outputs to match their probability score. So this is called the soft loss function. Well, you also have your ground truth label. So ground truth label is 1 or 0. It's binary labels. They also call it hard labels. So soft label is probability score between 0 and 1. Ground truth label or hard labels is a binary label, say 0 or 1. And then using the 0 or 1, you can also to calculate what is the hard loss function. So that the small model trying to get close to the ground truth labels as much as possible. So this is a distillation overview, and then the loss function is usually a weighted loss, right? So between the hard loss and soft loss over there. Yeah. So this is usually how distillation is played, so that we want the small model to catch up with the performance with the big model. So using the 5 teachers, right? The teacher model is trained on 4 folds, right? And then we use that model to predict the remaining 1 fold, and then to connect the win rate probability score over the holdout data sets. And that creates the soft labels to train the small model. And also they do some manual review as well, because they think there may be some human mistakes in the annotation. So if the teacher model say response A should win while the humans say response B should win, then there will be a disagreement. So they will also do some manually review some samples in the high disagreement to correct the mislabel pairs. Oh, so as I mentioned, right? So the teacher model, they just trained with trying to be as high as the quality as possible or human annotated data. Well, when they train the student model, you see how many data sets they use. So they use so there are a set of data sets that has hard labels. Well, also because small model is faster and easier to train, right? So you can train that over a bigger data sets. Well, the big model is like takes more resources and slower to train. So it makes sense that they just fine tune it on 100K. Well, in the small model, yeah, no limitation, just throw in all kinds of data. They are able to find publicly. So this is all they are able to find the data sets with hard labels, meaning that no matter it is from humans or from say the GPT-4 or judge, right? So if but it's still like an open data set. Then so this data set has the winning labels. So all the public data sets they can find. They also have some data sets, there's no winning labels, but they have the responses. So this V1, V2, and V3, it seems is from the first competition of user preference modeling in the past. So they take that problem, right? So you have the problem, you have the response A and the response B. Then they run it still. They use the teacher model to label this data set, even though you don't have the winner label there, right? You have no winner label here, but you can use your teacher model to decide to get the soft scores, right? To get these soft labels for these data sets. Yeah, so this is like so this is like kind of like a synthetic labels. You can get from the teacher model. Yeah, so this dataset, like the LM sys chat 1 million dataset, I think, yeah, so they specifically focus on, because I think this dataset, the responses coming from a lot of LLMs. So they just limit the LLMs to Llama, Qwen, and this V2 chat, ASIN V2 chat LLM. So they limit the responses to this few LLMs and then use the teacher model to provide the soft labels to train the small model. Yeah, so that's the logic, right? So teacher model only train a small data set with as high is the quality as possible. And then the teach student model, you can choose to train on all the available public data set you can find. No matter it has the winner label or it doesn't has the winner label, you can still use the trained teacher model to provide the soft labels and also the synthetically generated hard labels, right? Because once you have the probability score, you can choose, say, 0.5 as the threshold to generate the synthetic hard labels as well. Another interesting they mention is the final distilled model is a linear merge of the two models. So one is trained on the full data. Full data is including all of these data sets with hard labels and no hard labels. So it's trained on all the data set. The other one is excluding the last two data sets because the last two is synthetically generated, right? The labels, because there's no winner label. The label is just generated by the teacher model. So they train they train also another one just with the data sets with the winning labels included. So I would say the full data is lower quality with some synthetic labels from the teachers. And then the second model is like just trained on the the data sets that has the winning labels included. And then they do a model merge. Ideally, I think these two models, the parameters may not that be different, maybe has some slightly difference. Anyway, so this is like because these two are exactly the same model, right? The same artifact there. So it's very straightforward just to do kind of like linear weights or linear interpolations of the two models to get the final uh, weights for the merged model. Model merging is also very interesting because model merging kind of also usually plays a role of the regularization as well, because you can think of this theta A as the regional model weights and theta B says the updated model weights. So you do the model merging so that you're trying to still, keep as much as possible, say, by adjusting the alpha to be a high ratio, 0.9, right? Still want to keep the majority of the weights from the original model while still do allow some small updates on the original model weights. So yeah, so that's the idea, depending on how you want to set alpha over here. I think
Yeah.
they must fine-tune the alpha based on the data. Let's see.
Okay, can I ask a clarification question? Are these model updates or is the actual label in the end when you do the prediction, you do a linear interpolation of those?
Uh, in my guess, is the merge of the model parameters due to the inference time limit they have, right? Like if you do not do the model merge, basically the same model, you need to run it twice on the full test set. But if you do the parameter merge, you just get one merged model, like final distilled model. You just got one model, you just don't do the pass once. So that will save the inference time in the end.
Okay, and these models are the same architecture, just it depends on what
Yeah,
data
what
set you're
data
training.
they choose. In my
Got it.
guess, it's like one is lower quality, one is a higher quality data. Yeah.
And this is done at the very end, right? Not during training. This is done
Yeah,
at the
not during training. It's
inference.
at
Okay.
the end. Yeah, just a linear merge. This is my guess though, because they haven't fully described
Yeah.
what does a linear merge mean. But this is my understanding from from my guess. And also based on how they, for example, how they described about the inference, right? So they do two inference passes. Again, the two inference passes not say do inference on two models. They do is like first using the merged model on all sample, right? So you get this means that it's just one merged model, it's not two models. The second time they do a response order swap because people find that the preference, depending on which response comes first, you may get a different results. Like if the response A comes first in your input before B versus B come first, you may get different preference output. So basically the second time they only run on the most uncertain predictions and just swap the order of the response A or B. And then to see, and then I think then they merge doing the example of the final probability scores for this 33, so 1/3 of the most of the full all data sets. So this is like 1/3 of the full test set that has the most uncertain predictions according to the first pass. Yeah. So I think they choose why they choose 1/3 and not doing it on all the test data is also because the inference constraint. So that they can reduce the, pull their inference time within the limit, right? So they just choose to rerun it, like swap the order of response A and B and just rerun it on the most uncertain predictions. Yeah, so this is what's their solution are in the end. Yeah, so even though I think it's not that clean, I would say usually Kaggle winning competition is not that clean. It's like an Olympics of, yeah, no matter how many data sets, how many tricks you use, performance is what they care about, right? So even though this competition also has some constraint on inference, so that's why they do the distillation and trying to really push the performance of the small model, student model there. So I think maybe this is not the, ideal design for production models, but I think all the tricks they put that they try are also inspiring in terms of how you want to develop a efficient production model there. And then, yeah, I do want to get back to the question already raised before. I believe there's a gap in the preference modeling, right? Because they tried, and also you can also look at other solutions. So if you go to the leaderboard, right, I think the five, at least the top six are open. Yeah, I think these are also, some are very different designs, some are using very different base model, and yet it looks like the upper limit is 71%. So uh, then why it is the case? Well, it can be the human labels are noisy. So in many benchmarks, even human annotators only agree with each other on 70 or 40% of the time. So this kind of defines the upper bound of the preference modeling performance, right? Because basically like humans disagree with each other. And yeah, so you have that uncertainty and variance in the labels provided. Then I doubt that if that is the case, I doubt the model can exceed beyond 80%. This is also because different annotators may label due to personal preferences, right? The moods they have, how they feel, biases, backgrounds, misunderstandings, what kind of things can contribute to the preference. Because human preference is also personal, right? You can write a SOP trying to unify, like trying to define the standards of human preference. But when you ask individual human to provide the labels, they can still, prefer it in a different way. So the labels can usually like genuinely just very diverse, conflicting with each other. So yeah, I think that is also understandable in terms of, just human preference overall. And also there can be ambiguity in the task definitions. Yeah, so basically the instruction needs to be clearer and it can be interpreted differently by different individuals. Yeah, and some are just very subjective preferences, right? Some human may overweight politely the human and humor, and some may prefer just helpfulness, how concise, straightforward that is. Right? If you hear the news that the OpenAI just rolled back a model that is just too flattering, just too polite, right, to human response, I think it's also an outcome of the human preference modeling that they somehow the LM learns that, oh, human likes to be flattered. Then the LM is just making too much nonsense there without directly getting straightforward to the answers that that is expected. Uh, and then there will be also some model mismatch, but I think these two may contribute the most to why we observe like 71%. I think there's still some model aspect. Maybe the model lacks a capacity because right now I think just the model itself is a small model because that is the constraint that the competition put. So if you use a larger model, maybe the performance can jump to 70, say 75 or 78, or maybe around 80%, like getting closer to the human agreement upper limit, right? So that can be still some room to improve with a larger model. And also you may need to some additional features, right, to model the preference, not just the response and the prompts, but you can also input more signals such as the background of the labeler of the user. So basically, it's more like a personal modeling in that sense, so that you can further improve the personal preference modeling with those additional signals. And to really improve this, you may need cleaner and better instructed label data. And you may also want to incorporate personalization or more context in the preference modeling to be more personalized. And also, people are still exploring to say how they can refine the learning objective so that they can better align with the human preference training in the end. I think the objective, yeah, sometimes it's just hard to quantify what human really likes. So, yeah, so I think there will be more work coming in this direction of how to derive this more, define these objectives to better capture the human preference.